We're going to take a look at a little bit of the theory behind solving higher order linear differential equations, some of the things that we need to be aware of and what we're looking for. Now, before we start talking about maybe higher order linear differential equations, we got a few definitions and terms and stuff to get out of the way. First thing I want to talk about is something called an operator. In this case, a specific type, a linear operator. Now, an operator is really anything that changes one thing into something else. One of the easy ones that we've seen is the derivative is an operator, right? Because it changes one function into another function. Now, generically speaking, I'm going to be talking about all operators, like the integral is an operator, multiplication can be thought of as an operator, all the operators at once. So I'm going to give the operator a generic name, and I'm going to call it L. Now, it's got to be operating on something, so I'm going to say that something is some y, some function of x or whatever. Now, a linear operator has to have some very specific properties, and it's basically two. To be a linear operator, if you're doing the operator on a constant times your function, then you have to be able to pull that constant out in front and not affect the result of the operator. The second one is, if you're operating on two functions, let's say y and z, who knows, it could be plus or minus, then it's got to be L on y plus or minus L on z. Right? So again, think of like your derivative, right? If you have functions that are joined by plus or minus, you can just take a derivative of each one of these. If it has both of these properties, then it's considered a linear operator. Most of the operators that we're going to deal with in this course are linear operators. That's why it's going to be important. So let's say, that's our definition of linear operator. We're going to be talking about the linear combination of things. Now, a linear combination basically is kind of putting these two ideas together for an operator. What does that have to be linear? Well, you have to be able to pull constants out front or multiply by a constant, and it has to be separated by addition or subtraction, or that's not effective when you do it. So let's say that we have a set of things. Let's call them, I don't know, U1, U2, U3, so on and so forth forever. A linear combination of these would be kind of applying these properties. I'm going to take each one of these things, whatever they are, I'm going to multiply by an arbitrary constant, and then I'm going to add them all up. So a linear combination would be like C1U1 plus C2U2 plus C3U3, so on and so forth forever. So how do you make a linear combination? Most of the time these things are like functions or vectors or something along those lines. You just take each individual thing, multiply by an arbitrary constant, then add them all up. Now we're going to run into this for the rest of the semester. We're making linear combinations all of the time. One more major idea that we need from here. Let's talk about something called linear independence. All right, scary sounding, linear independence. Let's say we have a couple functions. I'm just going to start out with two functions. Let's say we have the functions y1 and y2, two different functions. y1 and y2, well, if we did a linear combination of these, it would look something like this. That's a linear combination. y1 and y2 are linearly independent if the only way this is true is if both C1 and C2 are exactly 0. Basically all it's saying is here, y1 and y2 really aren't constant multiples of each other. That's kind of the way to think about it. Now, of course, you can do this with 3 functions, 4 functions, a million functions, doesn't matter. It's the same exact idea. However, to test this, we're going to use something called the Wronskian. By the way, just for shorthand notation, LI. If we're going to test for linear independence, we're going to do what's called the Wronskian. here's what the Wronskian notation is. You start with a capital W, and then you put the functions in parentheses, so y1 and y2. Well, what the Wronskian is, it's going to be the determinant of the matrices. Now remember, you can only do the determinant of the matrices if it's squared, where you put the functions in the top row, the derivatives of those functions in the second row, and find this determinant. If it's not zero, then y1 and y2 are linearly independent. We're going to see why that's important in a second. However, if it does equal 0, that means they're linearly dependent. Now, the Wronskian scales up for no matter what size you need. If we had 3 functions, y1, y2, y3, well, again, we put these across the top, y1, y2, y3. The next row would be the derivatives. Now remember, since we can only do the determinant of a square matrix, we need another row, so do another derivative. y2 double prime, y3 double prime. And if you had 4, you'd have 4 rows, which is all the way down to the third derivative, so on and so forth. So this just expands on down. So let's see if we can see what I mean by this. What if I said, determine if sine x and cosine x are linearly independent. Now, for some of this, when we're doing basic functions, you may be able to reason out on your own that they are, especially when you only have 2. Can you take the sine function, multiply it by a number, and get the cosine function? Of course, the answer is no, so they're not linearly independent. And you can see that the way that this would work out, notation looks like this. We're going to do the Wronskian with the sine of x and the cosine of x. Put the functions across the top and their derivatives across the bottom, and find the determinant. So we multiply down the main diagonal, that's going to give me negative sine squared x, minus multiply down the off diagonal, cosine squared x, which is negative 1. All right, this is not 0, so these two functions are linearly independent. Okay, so very, very simple to test to see whether 2 functions are linearly independent or not, or 3 functions, or 5 functions, whatever. Now, of course, the more functions you get, the more work the Wronskian actually ends up being. But just plug it in, find the determinant. Now, it doesn't have to be a number. It could still be a function here, but if that function is not exactly 0, then they are linearly independent. Now, what I mean by exactly 0, let's say you did the Wronskian and you got x squared out of it. Now, x squared can be 0, but it doesn't matter. It's not exactly 0. If it's exactly 0, then they're linearly dependent. If it's anything else, then they're linearly independent. All right, so let's see if we can put a few of these ideas together and see why we went through a few of these definitions. We said that we were going to take a look at higher order linear differential equations. Okay. So, let's take a look at nth order linear differential equations. Now, I'm going to write this out, and it's going to be kind of messy. Let's see if we had a sub n plus a sub n minus 1, y n minus 1 plus all the way down, we'd have a1 y prime plus a naught y is equal to 0. Now, all the a's are functions, and those could be functions of x. They could be constants, they could be stuff that have x, and those are just functions. And of course here, this is the nth derivative, so that's the highest derivative, so this is an nth order linear differential equation. Now, since it's equal to 0, this is called homogeneous. Now, unfortunately, the word homogeneous gets used in a lot of different ways and a lot of different subjects. For the rest of the semester, homogeneous for us just means equals 0. So if we ended up having this exact same equation, all the way out to a1y prime, a0 y is equal to some function of x, right? If we have something that just has x's in it, that means it can be isolated on the side. This is called non-homogeneous. All right, so depending on whether the function, our differential equation is homogeneous or non-homogeneous, we're going to have to approach them slightly differently, kind of, a little bit. All right, so these are nth order linear differential equations. One is homogeneous, one is non-homogeneous. Now, either way, you can think about it like this. Since this is an nth order derivative, you'd have to integrate n times, which means you would get n arbitrary constants. So if you wanted to know the exact solution, you would need n conditions, either initial conditions or boundary conditions. Now, how do we represent that for... We're just going to talk about the initial conditions. You would know something about the function at some initial spot. Let's just equal some y naught. You'd know the derivative at that spot. I'm just going to call it y1, all the way up to the n-1 derivative at that spot you would know. So for the initial conditions, you'd have n of those, and you'd have to know from the function all the way up to the n-1 derivative evaluated at a single spot to come up with all the arbitrary constants you would get from solving this differential equation. Now, of course, if it's equal to 0, it's homogeneous, and it's not equal to 0, some function of x, it's non-homogeneous. So let's start out with something like, let me go ahead and put this down here. Another factor we're going to need to know that's extremely important, I'm going to put right here, a nth order linear differential equation has n linearly independent solutions. Now, that's an incredibly important sentence here. An nth order differential equation has n linearly independent solutions. That's let us know how many solutions we have to find before we're done. Now, this is related quite a bit to polynomial equations, and we'll see why it's kind of related in the future. Like a fifth order polynomial has 5 solutions. A 7th order polynomial has 7 solutions. Same idea here, right? A second order differential equations will have 2 solutions. Now in this case, they actually have to be linearly independent solutions. So, the set of all the linearly independent solutions is called the fundamental set. Okay, so if you find all the solutions and you put them into a set, then it's called the fundamental set of solutions. Okay, let's take a look at a differential equation here real quick. Now, we don't know how to solve this yet. Let's just say it's this. Now, this is a second order linear differential equation. We could probably get around and find a way to solve this, but for right now, we're going to say we don't know how to solve it. But let's say I told you this. What if I told you the 2 solutions, y1 was sine x and y2 was cosine x, what if I told you those were the solutions? Well, first off, how do you prove that something's a solution? Well, you'd have to plug it in. So you'd have to have the derivatives here. And y2 double prime would be negative sine x. And if you plug this in, y2 double prime plus y2 equals 0, well, that would be negative sine x plus sine x is 0. So you see sine x is a solution to this differential equation. You could check the second solution. So we said y2 prime would be negative sine x y, what did I get 2 here? These are 1s. Sorry. Y2 double prime would be negative cosine x. So if I said y2 double prime plus y2 equals 0, well, that's negative cosine x plus cosine x is 0. Notice that also works here. So both of these guys are solutions. Now, how do I know that I've found all the solutions? Well, we need 2 more pieces of information. First off, this was a second order differential equation, so I was expecting 2 solutions. Also, I would need to know, are these linearly independent solutions? And lucky for us, we already tested that. We know that these are linearly independent. So the fundamental set of solutions for this would be the 2 functions sine x and cosine x. So to justify it's a fundamental set, you have really 3 things you got to do. You got to check to see if each function is actually a solution by plugging it in. You got to make sure you have the right number of solutions that's based off the order of the differential equation, and you got to make sure that the solutions are linearly independent. Once you've done that, you've found the fundamental set of solutions. Now, a few more things that we're going to need when we're actually comprising our entire solution is the idea of superposition. Scary sound, but really superposition just means that you can put together a bunch of solutions in a linear combination and there's still a solution. Here's the idea. Does it make sense, first off, since the derivative is a linear operator, that if y1 equals sine x is a solution, and I'm still talking about the same differential equation up there, then y1 equaling, make up any number you want, 7, would also be a solution. Well, let's check it real quick. If y1 is 7 sine x, y1 prime is 7 cosine x, y1 double prime is negative 7 sine x, and when we plug it into our differential equation, we still get 0. So notice the constant here didn't make a difference to whether or not it was a solution. The reason, oh, I say not equal 0. The reason is because the derivative is a linear operator, so the constant multiple doesn't make a difference. Now, also because it's linear, what if I added these 2 together? Would that still be a solution? What if I said this? What if I said, let's let some function be sine x plus cosine x? Basically, all I did is I just added those 2 together. Well, if I take the derivatives here, y prime would be cosine x minus sine x. Y double prime is negative sine x minus cosine x. So y double prime is negative sine x minus cosine x plus sine x plus cosine x. And it's obvious to see this is 0. So not only does a constant multiple of a solution is still a solution, if you take solutions and add them together, it's still a solution. So the most generic way that we can write a solution is a linear combination of all the solutions. So represent the solution to a homogeneous linear differential equation as a linear combination of the fundamental set. Okay, now this solution we generally call it the complementary solution. And we denote this y sub c generally. Okay, so if we come back over here, we just decided that to this differential equation, the fundamental set was sine x and cosine x. So we would generally say the complementary solution to this would be some linear combination of these two. And it doesn't matter what order you write it. So it'd be like some c1 cosine x plus c2 sine x. In any order, whichever one, right? This is still a solution to the differential equation. You don't believe me? Plug it in and you'll see it works out exactly the same way. The only difference is you're going to get this line right here, but you'll have C1's here and C2's there, which means it's just going to cancel out. So we always represent the solution to a homogeneous equation as a linear combination of the fundamental set of solutions. So that gives us what's called our complementary solution. Now, what if we were talking about a non-homogeneous differential equation? So let's say I'm going to change my equation here just a little bit. Y double prime plus y is equal to x. Well, here's the interesting thing. This solution to this differential equation is actually made up of a couple of pieces. It's made up of the complementary solution, because imagine I can plug this in to this side and it gives me 0, right? So that doesn't affect what it equals on this side. But then I have to also find a solution that will actually produce x on this side. We generally call the solution to the non-homogeneous the particular solution. And we denote that y sub p. Now again, this one's one I'm just going to do by inspection. Does it make sense that y sub p is just x? Well, we can check it real quick, right? Yp prime is 1, yp double prime is 0. If we plug it into there, we get 0 plus x is equal to x. X equals x, so that is the particular solution. So when we have a non-homogeneous differential equation, the complete solution to the differential equation, we're going to use, what I said before, superposition. We're going to use a combination of our complementary solution and the particular solution. So the complete or general solution to a non-homogeneous differential equation, y, is equal to the complementary solution plus the the particular solution. So for this particular example here, those are homogeneous, and then this was the non-homogeneous. For this, the complete solution for this, or the general solution, would be the homogeneous solution, or the complementary solution, which we said was c1 cosine x plus c2 sine x, plus our particular solution, which would be x. Now this should make sense that it should work, because we know that these two pieces, if we plug them in, give us 0, and we've already seen if we plug the x in, gives us the x on the other side. So that's the way that we are going to represent solutions to our differential equations for, well, the rest of the semester. We're always going to look for the homogeneous solution first, and then a particular solution second, and then we're going to combine those two using the concept of superposition, that the sum of solutions is still a solution, as long as the operator is linear, to give us a complete solution or a general solution to that differential equations. Now, once we have the complete or general solution like this, now is when we would apply any initial conditions to try to figure out what the arbitrary constants were in our differential equation. So a lot of theory here. Over the next couple of weeks, we're going to see how we're going to apply all these ideas.